Yeah, so I'm Oskar, and as Bodil said, I'm working as a Haskell developer for a company called Empowered. Today I'm going to talk a bit about finite-state machines and kind of what your compiler can help you with, or more specifically, what your type system can help you with. And this is the sort of trip we will be making today. So I generated this nice fantasy map to make you very interested. And we'll start down in the Valley of Programmer Death and escape the land of implicit state through ADTs and go through the side effects into the safe harbor of MTL style. And pick up some type classes, travel through Indexmonads, and we will cross the value type level boundary into the land of Idris, where we will eventually settle down on the type-safe shores and reflect on our journey. Yeah, so this will be a fast-paced tour. I have a lot of stuff to show you, and I hope I don't keep you from lunch too much.
Don't worry, I'll stop you.
Okay. And yeah, I hope I can inspire you to learn more, because there are a lot of paths to take here and stuff to check out. So first off, we'll talk a bit about state. And a stateful program is one that remembers its previous events. And we call that memory the program state. It may transition to other states based on what it has seen before. And one problem with stateful programs is implicit state. And with implicit, I mean that the program does not explicitly define the set of legal states. And state may be scattered across many variables all over the place, and you can't really follow the program in what state it kind of transitions between without reconstructing that knowledge from all those variables. And you might do a lot of runtime checking and asserting that you're in a state because you have to be sure. So instead we can make state explicit, which makes it more clear how we transition between states and how they are constructed. And it can make stateful programming less error-prone. And one technique is finite-state machines. So with finite-state machines, we model a program as an abstract machine, which has a finite set of states, and the machine is in one state at a time. Events trigger state transitions, and from each state, there's a set of legal transitions expressed as associations from events to other states. And many of you have surely heard of finite-state machines before in some sense, or have a relation to them. And yeah, there are a lot of different takes and ways to look at this. So for this talk, we will use this simple model that I've stolen from the Erlang documentation. And since there are a bunch of Erlang programmers here, I think, at this conference, I'm trying to get a good start here. So let's use that. And it says, if we are in state S and event E occurs, we should perform the actions A and make a transition to state S prime. So it's very simple. And even if this looks like a function up there, this is like the conceptual model. We won't necessarily write everything as a big function from a pair of state and event to actions and another state. So this is our definition, and we won't be talking much about like a million more machines in the strict sense. We won't be doing hierarchical state machines. We won't use guards on transitions, and I won't go crazy in doing a lot of UML state chart stuff. So don't be afraid. What we will do is to model the set of legal states and events as data types, and preferably we will use Haskell. And in this way, we will have, each state will have its own value constructor. And you can do this or similar things in most mainstream languages as well. So we will start by encoding using algebraic data types. This is the example I want to use for most of my code coming up. So this is like a shopping cart checkout flow. You've probably seen these before, and this is one of the kind of canonical examples of state machines at a like business process level. The checkout begins with having no items, and then one or more items can be added. After that, you can start the checkout, and all the states in this big box called checkout can be canceled from. So that's what this is really the hierarchical notation, but yeah. So you can cancel from any of those free states in the box. We start by selecting a card, going from no card to card selected, and then we confirm it, and then eventually we place the order in which we have reached the terminal state. So this is a bit simplified, but it will illustrate some of the points I want to make. This is our state data type, and it has one constructor for each valid state, and some of them are nullary, which means they have no arguments, also known as constants. And some of them have arguments like a non-empty list of cart items, and when we kind of accumulate state, we get more stuff, so we end up having a card, and in the end, we just have order placed. The events are also data type, and similar thing going on here. Some have an argument, some don't. So one constructor for each event. And our first attempt of implementing this would be perhaps a function like this, saying that a finite-state machine is a function from state to event to state. And we parameterize that by S and E, so state and event types. And then we go on to define checkout. And yeah, this doesn't look too bad. This is very similar to like the definition from Erlang that we looked at. And we can pattern match on the current state and the event and do some decision. So there we have our transition function, so to speak. And the problem is, in our case, that with this setup, we cannot interleave any side effects in between. When we transition from one state to another, we can't have side effects because this is a pure function. Or could be at least, but let's say that this is a pure function. But we instead say that we need an impure function. So we have a state machine be a function from state and event to I/O of state. And now we can perform side effects on state transitions. So let's rewrite this checkout thing with the impure FSM instead. The first pattern match creates a non-empty list with the first item. The second one just adds an item to the list, so on. Then there is a bunch more I'm not going to show you. And the last one will, given that we have some way of charging the card with this payment provider thing, we can do a side effect, and then we can return the terminal state. So how would you run this thing? A very simple runner could look like this. Run impure takes an impure FSM, initial state, a list of events, and returns the terminal state in I/O. And the definition is really just fold M. Very simple. We could easily decorate it with stuff like logging. So this function takes an FSM, returns another FSM. What it does is it runs the one it took and logs its transition and return that state. So when we run this, starting from no items, and with these events in the list, we might see this. This is the output we will see. And my implementation of the payment provider just prints charging some amount. So here we see that the side effect is interleaved between the transitions. To summarize this part, we have explicit states and explicit events using data types. We can provide stuff like standardized runner, logging, metrics. We might, instead of having a list of events, we might use the pipes library or conduit or what have you. Some other way of kind of feeding the events in. But one problem is that transitions are coupled with I/O currently, which with that we can't test the state machine in a pure setting. So that might become a problem. And while illegal states can't be constructed because we have our data types, illegal transitions between states can be made. So we can make a mistake in our implementation and do an invalid transition between states. And the compiler wouldn't be angry about that. So could we get some more flexibility around testing? And could we get some stronger guarantees about our program actually following our model? So we're going to use MTL style, as is known, and we're going to use associated types. So this is like a kind of extension to MTL style for state machines. We will write our state machine in this MTL style, which you will see soon. We will have these extra conventions for state machines, which I'll describe. And with this, we can combine it with the stuff like monad transformer, regular monad transformer stuff like error handling and logging and so on. And we can build higher level state machines out of lower level ones. So we get some composition out of this. You might explore using extensible effects or free monads or something else, but I've chosen to do this with MTL style. And we start out writing a type class which encodes the state machine transitions and its events. And each event is represented as a method in the type class where the current state is passed as a value to that event, and the event returns the resulting state. The state type is abstract using an associated type alias, and this is, so in our kind of model, our type class, we don't know the concrete state type. We write a program depending on this type class, and then the type class and the program together kind of forms our state machine. Then we need an instance to run the state machine program and actually have some side effect. So the instance perform state transition side effects is the one actually doing, like, charging the card. The instance chooses the concrete data type for the state. So the instance can have its particular implementation details going on inside the state that gets passed around without the abstract program knowing anything about that. And we can write these instances for testing, like instances that are free from side effects. So we define our states as empty data types in this model instead. These data types have no constructors, so there are no values inhabiting those types. And we will write our checkout type class, which will contain all the events and their state transitions. And it has this associated type state of M, which has kind star to star. How many know the star to star notation and kinds in Haskell? Okay, a bunch. So if you don't know what this is, you can think of it as like a type level function and describing this type constructor taking, so star is basically type. So it's a function from type to type. And so the state of M will be some type constructor with one argument. Now let's look at some of these methods in the checkout class. Initial gives us just a starting state. It doesn't do anything more than that. Here we see this associated type being used. It's parameterized by one of these empty types that we have for states. In this case, it's no items. Some events are very simple. They transition from exactly one state to another. So confirm goes from card selected to card confirmed. Some events are more complicated. So if you remember from the diagram I showed you, both no items and has items accept the select event. It's the same name for coming from two states, the same event being accepted by two states. So we have to pass in either one of those states to we have to pass in either one of those source states to the select event. And we could use the either type for this, but I think it would be more clear if we create a specialized type for this purpose. So select state has one constructor for each choice. These are one constructor for each state you can kind of come from when you do select. And we pass such a select state value to select along with the cart item, and then we go to has items. Then there are three states accepting the cancel event. The either type would be even worse now, because then we'd have to start nesting them, and no, let's not do that. So we write a new data type called cancel state, which has three constructors, one for each valid state to come from. And we pass that in the same manner to cancel. this is the complete type class with all its methods. And to show you how it corresponds to the diagram, I've just put it on top. So they're very similar in what they say. You can imagine generating this diagram from type class somehow. And now we will write our program using this type class. So fillCart constrains M to be a monad with the checkout and IO operations. So I should point out that I'm actually using IO in this abstract program as well, just to kind of drive it forward. You could factor that out if you want to make it fully testable, but I've tried to keep it as simple as possible and only have the state machine be abstract in this example. So the type signature says that this transitions from no items to has items. So, and the definition asks for an item and selects that. And you can note here how we wrap the state in the appropriate no item select constructor to get a select state value. And finally, fillCart hands over to select more items. And that signature says that it remains in the has item state. Its definition asks the user, do you want one more item? If so, selects that, and then it recurses. So it keeps on spinning here. If the user doesn't want any more items, then we return the state we have. Start checkout type signature says it transitions from has items to order placed. And that matches kind of what we have so far. We ask for a card and for a confirmation. And you can see here in this do notation that as soon as we transition state, we get a new state back, and we have to start using that instead. So we kind of swap the old state for a new one and start using that, passing that into the next event, and so on. And as these state values, their types are, they're using the associated type. So we don't know the concrete type, which means we can't construct these states and kind of cheat our way through onto the end. We have to perform all the steps. And in the end, if the user confirmed, we place this order. So, and if they didn't confirm, we cancel, and we go back to possibly selecting more items, restarting the checkout, and on and on. This is the main program starting the whole thing. It creates a checkout flow, runs it, and then ends it. And what we get back is like the monadic return value, that's an order ID. And so far, we have only seen the abstract part of the program, and we need an instance as well. We only depend on this checkout type class. And together, this program that I've shown you using the type class and the type class kind of form the state machine, like the model or the abstract part, how it will run. But we haven't actually done any side effects yet. So we need this instance of checkout to perform the side effects. And it will also decide this concrete state type. It will perform the appropriate effects at each transition. And we will run this to run the checkout program using this instance. First, I'll show you the concrete state type. This is a bunch of code. Don't be scared. I'm using a GADET here. That's a generalized algebraic data type. So it has a parameter s, which we can parameterize it differently with the different constructors. So each constructor here maps to one state, and if you see no items here, that's not the same as, no items on the left. The constructor named no items isn't the same thing as no items the type. No items the type is that empty type that we created way back. So here we kind of link this concrete constructor for this type to that empty data type from before. And this creates like a mapping between these constructors and the associated type and our empty state types. So it's a bit confusing perhaps, but you will see how it comes together soon. And maybe you don't see it explicitly here, but the checkout state has kind star to star, so that matches the associated type in the type class. Given that we have this new type, CheckoutT, this is like the MTL stuff you just have to do and a bunch of deriving and boilerplate. then we can create an instance. And here comes the kind of tying things together part. So CheckoutT is an instance of checkout. And we say that the state type for this instance, for CheckoutT, is the CheckoutState data type, the getIt that I showed you before. So here we kind of link everything together and say, when we run this, the concrete type will be this getIt. So I'll show you a bunch of these methods, or the implementation of these methods. So initial just returns no items, no side effects. Select prepends an item to a new or existing list, depending on where we came from. And notice how we work with our concrete data type here. Those no items and has items, that's the constructors from the getIt. And we don't have to handle any mismatches. We don't have to say like, okay, and if state isn't one of these two, then we have to abort or whatever. Because the GHC will know from the getIt and the associated type that this pattern match is, or this case expression is exhaustive. So that's kind of nice. Place order generates an order ID. It calculates some price and charges the cart. Finally, returning the terminal state. So here we do some side effects. We run this abstract checkout program using run CheckoutT, and we end up in IO. And yeah, just print something. We could write other instances for testing that won't charge customer cards. And one thing you might be asking, like we have only driven this program by user input, but you might have stuff like timeouts and whatnot. So I'll show you a quick example of doing timeouts as well. So the example is similar to the checkout, but a bit different, a little twist. This is like a flight booking, where we select the flight first, and then select the seat. And the seat ends up being reserved for 5 minutes. And then after 5 minutes, it times out and going to seat released, unless the booking has been canceled or the seat has been paid for. In those cases, we end up in terminal states. If the reservation timed out, we can either cancel the booking or restart with the flight selected. So then we kind of go back to just having the flight and we start over. Like before, we use these empty data types for the states. We model multiple states accepting events with specialized data types for that. So that's the same as before. And the entire class looks like this. And there is really nothing new going on here from what I've shown you before, except that it's a different domain. So I won't go through all these again. These are events and their state transitions. Now let's look at this flight booking program. Don't worry about this monad-based control that came in. It's just some plumbing that I'm using for doing the actual timeout. This program is the entry point, so we're starting kind of top down. And we start by selecting a flight number, and then we pass over to with flight selected. In with flight selected, we select the seat. Then we start the timeout for the confirmation to actually buy the seat. In a real system, we probably wouldn't just ask the user, do you want to buy, and then they have their ticket. But we'd start a real checkout flow. But I tried to keep it simple. And we wait for an answer for this timeout. And it can have 3 different values. Sorry. So just true means that we got an answer and that it was a confirmation, a positive confirmation. I want to buy this ticket. So we transition into seat booked and end the booking. Just false means that we got an answer saying, I do not want to buy this ticket. So we cancel the reservation and end the booking. And nothing means that we got no answer in time. So the reservation timed out. We transition to seat released and asks if the user want to restart. And if they want to restart, we do that and recurse. If not, we cancel and end the booking. To summarize what we have seen so far with MTL style, we have modeled our state machines using these type classes and MTL style. We have used associated types for states. We've used explicit state values passed and returned from these event methods. And we have written part of our state machine as an abstract program depending on the type class, not as a big function from state and event to state. We are using instances for side effects. This is stricter than the ADT-based version in that we don't only encode the valid states, we also encode the valid state transitions. But it isn't necessarily safe because state values can be reused or discarded. And side effects can thus be reperformed illegally, which isn't good. There is nothing even enforcing a transition to the terminal state. We can just not do anything more and the compiler wouldn't know. So an example of reusing state values would be this. Here we first pay for the seat and charge some money, and then we discard that resulting state. Then we pay again, taunt the user a bit, and end the booking. And this is probably not in our business model, and wouldn't it be good if the compiler would be angry at this point? So one solution here would be to use something like linear types to ensure that a state value is used exactly once. But we won't be talking about linear types today. Instead, we're gonna move this state value inside the monad. So the monad will carry the state, and in that way, we won't have to pass around these explicit values everywhere. So the previous example would look like pay twice here, where we pay for a seat, and then we pay for a seat again, and then we get a type error because something is not correct here. We have, we've done a double booking, so to speak. To accomplish this, we need to parameterize the monad a bit more than before. We have to index it as it's known. So we use state types as parameters to the monad in addition to the return value. This is called Indexmonads. And as the name suggests, it's a monad that is indexed. And it's indexed by two type parameters, input and output. This can be seen as the type before and after this computation. And the type class looks like this. It's also an IX applicative, doesn't matter too much. But the IX monad is some M that has the type K to K to star to star. Sorry, the kind K to K to star to star. And the K here, the case, means that it could be any kind. And the two stars are types. So it says, like, the M takes two indices of any kind and a type, that's a return value, and gives you back a type. So to explain this index monad, hopefully quickly, I will compare it to bind from monad. So this is a regular monadic bind. How many here know kind of how this works? Okay, very good. Then I might pull this off. So this is dangerous area. Okay, I'll put iBind below here, and that's the index monad bind. So we add a bunch of indices, ij, jk, and ik here, in the kind of slots that didn't have them before. And okay, so what's going on here? If we add some colors and arrows, we see this very clearly. The input of the first monadic value is the input of the resulting monadic value. That's a red arrow from I to I. The output of the second monadic value is the output of the resulting monadic value. That's the blue arrow, K. And the J is like the intermediate index. That's a green arrow. So this is like the monadic bind, but the indices might remind you of function composition. So if you compose two functions, they kind of meld together, and the intermediate type in between goes away. You get one bigger function, so to speak. So this is iBind again, different formatting. To show you how we will use it or how you can use it, I'll specialize this type to states instead. So if we swap these variables for some state types, we have this instead. So one action from state 1 to 2, one from 2 to 3, and the result is all the way from 1 to 3 in one big chunk. And the last example here, we use two of our transition from the checkout example. So we have checkout and select card. And if we bind those together, we get one big transition from has items to card selected. So we hide the state value, and only the state type is visible in this monadic value, this indexed monadic value. And we cannot evaluate these computations twice unless the type permits it and kind of lines up. Oh, sorry. Okay, so in PureScript, now comes the PureScript part. PureScript has this row kind, which is really neat. You can think of this as kind of a type level record. And the reason why I'm using PureScript here is Haskell does not have this. So let's use PureScript for this example. And okay, row kinds are like type level records. So here we have a row of one field out of type file and one of in with a socket. This is a closed row, and they can also be polymorphic. So in the second example, we see a row that has at least out and in, and possibly more in this R row variable. And these can be used, and these are used in PureScript as indices for record types and for effects. So here we construct a record type using a row, and that's the same as the syntactic sugar below. That's the same type. And say we want to use these row types for state machines instead. Oh, I think I missed a slide, but yeah. The problem is if I go back, and that's the missing slide. Sorry, I should say this first. Okay, the index monads that I showed you before, they describe one state machine. You go from one state to another, and that makes it very hard to compose. So we might want to have multiple state machines going on in one program, in one computation. So some examples are opening two files. Then you have, if you see a file as a small state machine and you want to copy stuff from one file to another, you have two state machines living at the same time, really. And you might write a program like a ticket machine using card reader and a printer or, yeah, whatever. So what we want to do is to have a type that maps from names to states. Then we can have many state machines going on at the same time and use that kind of mapping as the index instead. So these named state machines can be independent, and we apply the events to them by name instead. And now we come to this part where we need these row types that I explained in the wrong order. And okay, so here we say, if we have these m's, we say that these are index monads. And in the first example, initial, we go from having some row to having a row with my machine added to it. So this kind of creates a new state machine value or resource. The second example transitions from my machine having state 1 to my machine having state 2. And the third example transitions or kind of deletes a machine that's in its terminal state. So it goes from a row with that my machine terminal state to a row without it. Then you could have a type signature requiring that each state machine resource is removed, or like that you have went to the terminal state. So this type signature run ix machines has two empty rows, that's a parens. And then we have to clean up and kind of go all the way through. There are some libraries implementing this, and now I'm going to shamefully show links to two of my own libraries. But the first one is ControlStay in Idris, which is not my library. But I will show this shortly. And the other ones are one for PureScript that I've been tinkering with, and the other one is for Haskell, trying to bring down the ControlStay ideas into Haskell. So if you want to learn more about these index monads in general, you can check out this blog, the Quang's Haskell blog, the Haskell package called Indexed. You can also use do notation with index monads if you're really daring. And you can combine this with session types, which kind of goes back to Chris Ford's talk from before. So for the last part, I will make a bit of an adventure and go into dependent types in Idris, this is like the craziest part that you can go for. So yeah, Idris is not currently recommended to use for anything like critical. You won't be basing your business on Idris right now, I think. And as Chris Ford, I think, mentioned, it's a hipster programming language, so gotta use that. And we can use some cool ideas from Idris and kind of bring them to Haskell or wherever, PureScript perhaps. So with dependent types, we can make some of these aspects around state machine implementations more concise. We can have better express that multiple states accept an event. We can do nicer error handling, and we can have dependent state types. And this ControlStay library implements this for Idris. And it also has this notion of named resources. But you won't be naming your resources yourself. You get like a unique identifier that you can use to refer to some resource in your computation context. And if you like this sort of stuff, you should read this Implementing State-Aware Systems in Idris, the ST tutorial. This is very good, and even if you don't know a lot of Idris, you can probably follow along here. So I recommend that. Okay, for this Idris stuff, we will use our checkout example again, but we will change it slightly just to leverage more Idris magic. We will merge the no items and has item state into one state, has items, which has this extended n natural number. So really, if you think about it, no items and has items is like, that's almost like a nat in itself. So we can just have one state with the nat saying how many items do we have, and we can start at 0. So selecting one more item increments that n, and when we check out, it has to be greater than 0. We start by writing this namespace for our protocol, and most of these things are like aliases for strings, like an item is a string and a card is a string and so on. And items of n is a vector of n. So it's a known length list, basically. Our state is a union type in Idris. And you see here the nat kind of flows through all the states until the end. So we always know how many items we have. The checkout interface has a state type as well. This perhaps reminds you of the associated type from the MTL style. And it's parameterized. That state type is parameterized by CheckoutState and gives you back a type. So very much like that associated type. In this interface, we have initial, which is an ST. That's from the library. So this operation adds the has items of 0 state and returns you a var that you can use to refer to this resource that's been created. Select takes a var and adds an item. And you see in the type signature that we go from having n items to having the successor of n items. That is one more item. And checkout takes a var, and the transition goes from has items of at least 1, that's S of n, to the no card state of the same amount of items. So we keep track of this number of items as we go along. Like before, we have free states accepting cancel. So in Idris, we can express this using a predicate over states, which is basically saying to the caller of this operation, please give me a proof that your current state accepts cancel. So we won't be using like a special data type that we wrap it in manually, but we will instead have this predicate at the type level, but yeah, everything is kind of the same level in Idris. So this data type says that, okay, a cancel state is parameterized by checkout state and a bunch of, or a count of how many items you have, and it gives you back a type. And there is one constructor for each valid cancel state. So here we use our valid states as parameters. And we link those nats together, saying like, if you're in no card n, then the amount of items you have is n. And in the cancel operation, we ask Idris using this auto keyword to, okay, can you give us a proof that the state S, because in the operation we take any state S, give us a proof that this state S is a cancelable state, and which, when we cancel from it, has n items. So the operation goes to has items of n. So this is why the number of items has to be tracked all the way through, because we have to go back in a known state. So instead of showing you the implementation of this checkout protocol, I will just show you a program using it. And select more is a function that selects one more item. And it depends on this type level nat to print a nice message, like, do you want to add your first item or one more? And yeah, it selects one item. Checkout with items goes from having from has items to order placed, or it stays in has items if the checkout is canceled. So you see this type level thing here, or else, where the type of this transition depends on the result, and the result is the return value, which is a Boolean. So or else switches on true or false, basically. So if everything went well and we did a checkout, then we end up in order placed. Otherwise, we still just have items. So we ask for a credit card, and eventually we place the order. And in between all those steps, we ask the user, do you want to continue or do you want to cancel? That's the longer lines. And I'm using some Idris notation to kind of short circuit out of the do notation if they want to cancel. But the cool thing here is that we couldn't do this continue or cancel in any other place than these three places, because we couldn't construct a proof anywhere else. Checkout or chop removes a resource in state has items. It will try to check out with items and complete the checkout flow. But if the user cancels, it will loop using Go shopping. In Go shopping, we select one more item. Then we ask if the user wanted to check out. If not, we go shopping again. And these two functions that I've shown you, these last two functions, they kind of go back and forth until the user has made a purchase. And the program is started like this. And you can note that all of these functions are total, which is a cool thing, because if you want to convince your boss that you want to use Idris at work, you can say that you can prove that your users will end up in the checkout and buy your shit. That's nice. Anyway, to have total functions that loop, we need to use this run loop forever. And the printing of oops, there is one partial value here, it's forever. And if we run out of foreverness, we print oops. So to summarize all this, implicit state is hard and unsafe, and just going the one step to making states explicit with the data structure is the big win. Really consider doing that. And you can lift more information to the type and get more safety if you want. You can do this in Haskell and PureScript and whatnot. And you can steal cool ideas from other languages. So do look at Idris and linear types and whatnot to be inspired. And as usual, it's no silver bullet. Don't rewrite everything like this, and don't hold me accountable for anything, basically. But yeah, the main takeaway is to reify your designing code and keep exploring. Thank you.